Hello, and welcome again to my Physics Online video lecture series. Today's videos, we're going to be going through the sort of predictions of Maxwell's equations. At this point in the semester, you should have already watched my video discussing the Ampere's law and Maxwell's modification to it, and how to find the magnetic field in regions in between the plates of a capacitor, for example. So what are Maxwell's equations? Or really, you could think of this more as what are Maxwell's predictions? Maxwell's equations as such are either integral or differential or both in nature, so there's a lot of calculus involved. And this is, of course, an algebra-based course that I'm making this particular video for. So I'm not really going to give you Maxwell's equations as such, although I'll summarize them in their algebraic form. Basically, Maxwell's equations, you should already be familiar with all four of them. Basically, what you have is Gauss's law for electric fields, Gauss's law for magnetic fields, Ampere's law with Maxwell's modification, and the Faraday law. So let's remind ourselves of what each of those are. Okay, the first one is that the total flux from an electric field through a closed surface is equal to the enclosed charge divided by this permittivity constant. That is also the first one that you learned. That's basically Gauss's law for electric fields. The second one is Gauss's law as applied to magnetic field. This one basically just says that the total flux of the magnetic field through a closed surface is zero. And as a reminder, recall that the flux of any generic vector field V is defined for us as that vector field V dotted with the area vector A. Okay, so if you have a closed surface, you may have to do that for multiple faces, or you may have to find some symmetry property, etc. In a calculus-based course, you would largely take an integral here. Okay, so these both are what we would call Gauss's laws for E field and for B field, electric field and magnetic field. Okay, the third of Maxwell's equations is basically your Ampere law. So that's the one that says that B dot delta L around a closed loop is equal to this permeability constant mu naught multiplied by the carrier charge that's enclosed by the surface bounded by the loop, plus again mu naught times the displacement charge, which is epsilon naught rate change of the E field flux. So delta phi E over delta T. And again, this is for a closed loop. So closed surface, you have a two-dimensional thing like a sphere or a cube or a pyramid. A closed loop, you have, a closed surface is a three-dimensional thing, but you're looking at the surface area, a two-dimensional effect of it. For the closed loop, you have something like a circle or a square or a triangle, and so it's a two-dimensional object, but you're actually just looking at the circumference or perimeter of that closed object. So you're looking at, in some sense, a one-dimensional quantity with your two-dimensional surface. And that is the Ampere's law, or sometimes called Ampere-Maxwell law. the fourth one is the Faraday's law. This is the one that says that the induced EMF, so EMF induced, is equal to negative N times the rate change delta phi b over delta t, rate change of the magnetic field flux. The N is in place because we're assuming that this is the flux through like one surface and that there could be multiple, for example, windings or something like that. So this right here is the Faraday-Lenz law. And Faraday's law is like most of this, the Lenz law is this minus sign here. Okay, so these are Maxwell's equations, and note that Maxwell did in fact help develop one of the four, excuse me. But why are they named after him? Well, essentially these equations make a set of predictions, and these predictions correspond roughly to each of these four equations, and they kind of unify them. So the first prediction basically is just that E fields start and end, or originate and terminate on individual charges. And so that kind of goes with the Faraday's rule for drawing field lines. So charges are the source of electric field lines as such. But a charge that's just sitting there gives you a stationary or static field, and a charge that's moving maybe gives you a moving field, or a changing field would be more appropriate. Okay, the second one is that B fields don't have any particular origin or termination point. So the field lines are closed loops. So B field lines form closed loops. And B fields are generated, or static B fields are generated by current. So B fields are generated by current, or moving charges. Okay. Now note that we've already said that E fields originate and terminate on individual charges and generated by those charges, and that if we move charges, then that kind of changes our fields. So these two statements already kind of mesh together to make a sort of prediction that if you're changing the E fields, that also produces B fields. So put differently, in order to produce a B field, you kind of have to change the E field in some way. Number 3, the Ampere's law. This one basically gives you the field in terms of current, but you could rephrase it to say that field can be produced not only by current, but by changing E fields. Okay, so B field is produced by current, or maybe we should say and, changing E fields. So if I have an E field that I'm changing, then that produces a current for me. Okay, prediction number 4, Faraday's law. The EMF, remember, is also sort of like E dot delta L. So this one actually predicts that an E field, or E fields, are produced by changing magnetic field. So now we loop back to these original two, and we have that changing an E field can produce a magnetic field, changing a magnetic field can produce an E field. And that's in some sense as far as we can get at the time of Maxwell because they didn't have a very good way of producing strong magnetic fields at that time. So it took another roughly 20 years before some experiments done by Hertz demonstrated these predictions. But taken together, what do these predictions do? So taken together, Maxwell's predictions can also predict another phenomenon that is outside of just these statements. We could say Maxwell's predictions call for the ability to sort of transport maybe we should say transport information about electric fields and magnetic fields without actually transporting any charges. So without transporting charges and therefore or current. So what does this sound suspiciously like? Where else have we encountered the ability to transfer or transport information about something without actually transporting the thing itself? Well, that is just what waves do. So this is what waves do. A mechanical wave, you'll recall, you just have like a vibration somewhere in the medium, and information about that vibration can be transmitted somewhere else in the medium so that you can detect it, somewhere over here without anything that's vibrating here moving to over here. So the same thing's going on with these electromagnetic waves. You have charges that are somehow vibrating, essentially. They're accelerating, really. And you're able to detect information about that acceleration somewhere over here, even though none of these charges make it to this other location. And the neat thing about electromagnetic waves compared to mechanical waves is that with mechanical waves, in order to have something happening here and you detect it over here, there has to be medium throughout these two, connecting these two locations. You have to have matter between here and here that can, this vibrates, and so the next one over vibrates, and the next one over vibrates, the next one over vibrates, the next one over vibrates, until this one vibrates. With electromagnetic waves, you don't actually have to have matter in between the source and the destination. You can move them through vacuum. All right, and so that is the essential prediction of Maxwell's equations that is added to the rest of physics over and above what these four equations themselves predicted, and that's why they're so relevant, or that's part of why they're so relevant. What Maxwell did was he predicted the existence of electromagnetic waves, and he tied together these four equations that previously had been considered four separate laws of nature into one coherent set of four laws that work together in nature. So if you combine the Maxwell's equations with the Lorentz force, which we encountered when I introduced magnetic fields and magnetic forces, when you combine these two sets of things, you basically have all of classical electrodynamics in one set of basically 5 simple equations. So that's it for today's video. Thanks for watching, and hopefully you've learned something and maybe even found something exciting within this video. So until next time.